So let's say we've been dealing with nice, easy situations where you have blank plus blank minus blank plus blank. It's all nice, fragmented. But what if you had something inside of something? Let's say you take the function x squared plus 2, but then you were to cube that whole thing. You can't do that. That's cheating. No, you can't do it. Well, you could. I mean, you could do it regular. And let's actually do that because it's a good example. So let's take x cubed, goodness sakes, plus 4. Here we go. We had some dying marker troubles, but I am back and we are still doing the chain rule. So this being said, we have, here we go. Before we do the chain rule, this is what happens when you don't use the chain rule. Oh man, we got x cubed plus 4 squared. What are we going to do now? Well, you can't work it through like this. You have to have it in discrete parts. So we've got to work it out the old school way, which means x to the 6th. Yes, x to the 6th. That is right. Plus, who is spreading? Plus, you have your 8 x cubed plus 16. There you go. And that's easy enough, right? And then you can go through and do your regular method. So you get 6x to the 5th, drop it, subtract 1, plus 3 times 8, 24, x squared, drop it, minus 1, and then 16 gets canceled out because it's a constant. Boom. So there you go. That is straightforward. It's not the hardest thing to do. I think I can erase these now. You guys are comfortable with them. However, what if we use the chain rule? You can do this a lot faster. The chain rule says that for any property, for any f of x, you can say that the derivative of it, so if you're taking the derivative of f of x, and let's say you have something inside of f of x. So, we take the derivative of f of x, and we then are going to go to g of x, f of x. This is a little complex, just hang in with me for a second. You replace f of x with u, so you're saying g of u, and then the derivative of u dash, or we'll make it du dx, which is the upper way to write derivative, du dx, is going to equal this if you're differentiating it. So the derivative of g of u times the derivative of the derivative of whatever this is times the derivative of whatever's inside will work. Hang for a second. I'll give you an example. You see what I mean. So with this, we're saying you have x cubed plus 4 squared. So the derivative of what's outside is going to equal 2 times whatever is inside. 2 times u. We're going to replace with u. The derivative of what's inside is going to equal 3x squared. 4 is a constant, you don't worry about it. So times 3x squared. 3x squared. You reinsert this for u, and then you finally get 6x squared times, what is that? We've got x cubed plus 4. And then once you work this out, you'll end up finding 6x squared plus 6 times 6x cubed will equal 6x to the 5th. And then over here, it's going to equal 24x squared. 6 to the 5th, 24x squared, 6x to the 5th, 24x squared. Same thing. You might say, well, it's not really much easier. It seems a bit more complicated. Why do I want to bother with it? Well, here's why you want to bother with it. Because sometimes this ends up happening. Hey, okay, we've got 4x to the 5th plus 3x squared plus 19 to the 6th. Try simplifying that. Have fun with it. It's not going to be fun because it's to the 6th. I would cover this entire board with the simplified equation for that. Okay, maybe not that bad, but it's not something you want to do on your free time. But if you use chain rule, all you get is you differentiate your whole thing, which will give you, and if you substitute this for u will simply give you 6u to the 5th times the different derivative of what's inside, which will give us 20x to the 4th plus 6x. 19 is a constant, we don't have to worry about that. Reinsert u, and you end up getting 6 4x to the 5th plus 3x squared plus 19 times to the 5th times 20x to the 4th plus 6x. Is it convoluted? Yes. But this is pretty much already simplified. You don't have to worry about working it out, because at this point working it out is just going to be a lot of work. If you wanted to, you could multiply this equation with the 6, simplify it a little bit more, make it more edible, but for most cases this is going to be a pretty compact and comfortable format. And notice the fact that this took about 1 minute. Going through this way and trying to simplify it, that's going to take about 10 to 15 minutes. So just a thought, if you're considering, should I use chain rule, should I not use chain rule? Use the chain rule, it's nifty. So again, let's give us an example when we do something like that. Let's say e to the 4x squared plus 6x. Okay, use the same rule. You say it's going to be u, so e to the u, that's just going to be e to the u times your derivative, which is going to be 8x plus 6. Now we're done, we can put it back in, which gives us 8x plus 6e, and then up on top you still have your 4x squared plus 6x. Done. Just that fast. And we'll do one more example with an ln. Say you have the ln of 4x to the 6th plus 9x to the 5th minus 3x squared. Again, you do the same thing. You don't even have to bother with the u this time. Just keep it in your head. So you get your regular, which is going to be 1 over 4x to the 6th plus 9x to the 5th minus 3x squared. And then multiply that by your derivative, and you can just put that right on top. And then that'll give you 4 times 6, 24x to the 5th plus 5 times 9, 45, 45x to the 4th minus 6x. Because you drop it. Boom. And that's all it is. Just that simple. Okay. And now that we have chain rule, what happens if things get even more complicated? And you have two entire expressions. Say you have a 4x to the, oh god, no one wants to go 4x to the 9th. That's too much work. 4x to the 5th plus 2x to the negative 3rd to the 4th. And then we're going to multiply that by, we'll just do it simpler here, times 6x cubed. Okay, so what's the time for now? Because if you try to use the chain rule, it's not going to work out so well. Because with the chain rule, it doesn't, having that multiplication makes it null and void. Because there is no form we've learned. There's no form of differentiation we've learned for multiplying x's together that doesn't involve simplifying yet. So what do? You use the product rule. And the product rule states that you can establish these I'm actually going to get out, must be the purple marker. You can establish two essentially separate bubbles, call them U and V. There we go. So you have your two separate bubbles and you're multiplying them together. And for that, for those bubbles, you're going to end up seeing your solution is going to be dy dx equals the first one, just the regular u, times the derivative of the second one, dv dx, plus the derivative of the first one times the regular second one, v, times du dx. And that's the product rule. Now, it kind of looks complicated here, but in practice it's actually pretty straightforward. So, we're going to run through this here. Now we know that we'll go over to this side of the board to work through it. So we see, first we have to find what our u is. Okay, that's u, just right there. So u is going to equal 4x to the fifth plus 2x to the negative third to the fourth. That's going to be multiplied by the derivative of v. Multiplied by the derivative of v, 18x to 18x squared. Plus your second term, which is going to be your v du dx. Okay, v, your standard, is going to be 6x cubed times then this monster. Hey, guess what, guys? We're going to have to use shade rule again. So I'll use brackets actually to make things a little clearer. Use brackets, and you'll see you get 4 times 4x to the fifth plus 2x to the negative third to the third times the derivative of what was inside, 20x to the fourth, minus 6x to the negative fourth. Whoop. Just barely enough space. And there you go. So you have your u is right here, times dv dx here, v here, times your du dx, this monster. If you notice, inside your du dx, you took your regular function, you differentiated it, leaving what was inside, and then you multiplied by the derivative of what was inside. And there you go. That, my friends, is how you product rule. That's all there is to it. One final thing we have to work through, though, is going to be the quotient rule. Woo. So, what happens when you divide it? Well, you could always go through it and say, okay, I'm just going to cheat, use my purple again, in the situation of 8x to the third plus x to the fifth cubed, let's say there, over 5x squared plus 9x to the third to the fourth. There we go. So here, now, I mean, you could use product rule. You could, cheat and push this up there to the side and say that 8x cubed plus x to the fifth to cubed will then be multiplied by this to the negative fourth. However, in situations where you don't have that exponent down there, you're going to get rid of this. It's sometimes going to be a lot easier if you just leave it and work it through it with the quotient rule. It takes away a lot of simplification when you're done, and it makes your life easier. So let's say in this situation, you could do this and put it to the negative 1 and then move it up there. But instead, we're going to use a whole new differentiation technique that's going to make your life a lot easier. So here we go. How the quotient rule works, bear with me, is that for any equation, if you have u over v, boom, Then your u over v will then go and become, when it's differentiated, u du dx times v minus du dx times v minus dv dx times u. Boom. However, it's not over yet because the whole thing is going to be over v squared. That's your quotient rule. Quotient rule, I will admit, is a bit of a monster, but once you're working through it, you're going to see it's not too bad. So let's take our original equation and figure out what our u and our v will be. So you have here, v's on bottom, here, u's on top, and we take it, we say, first things first, we've got our du dx, and we're going to work through it over on this side again. So first things first, we have du dx, and that's going to equal 3 times 8x cubed plus x to the fifth, because we're using the chain rule again, 2 squared times the derivative of what's inside, 24x squared plus 5x. Okay, so we have that. That's just the du dx. Multiplied by v, which is going to be, that works, multiplied by v times, and we'll come down here, v, which is just the bottom, 5x squared plus 9x cubed. Okay, there we go. I'll make this a dot for more clarity. And then, now we have our minus, don't have enough whiteboard for this, dv dx, the differentiation of that, which is going to be 10x plus 9/3, 27x squared, and that is going to then be multiplied by u, 8x cubed plus x to the fifth to the third. Boom. You're done. Ha! You thought. Because now we still have the v squared. You're not done yet. So this whole thing, your 3 times 8x to the third plus x to the fifth squared times 24x squared plus 5x times 5x squared plus 9x cubed minus 10x plus 27x squared times 8x cubed plus 5x plus x to the fifth to the third. It's a mouthful. Over v squared, which is at this point pretty simple compared to everything else we've gone through. 5x squared plus 9x cubed squared. There you go. Now, a lot of times quotient rule will not be this complicated because up here we had to use the chain rule, and that definitely made things take a little while longer, and we had double expressions on both sides. However, once you already get this all worked out, it is debatably faster than the product rule. Actually, it's not debatably faster than the product rule. If you had to work all this through the product rule with the -1 in the bottom, it would take even longer. So there you go. That is the quotient rule. So let's just review our rules real quick and see what we got here. So, number 1, we have standard. Standard method of differentiation, that's just your table. That's going to be your y and your dy dx with your ax to the n and your a n x to the n minus 1. Boom, basic result. Your e to the x and your e to the x and your ln of x with your 1 over x. Okay, that's all you have to worry about for standard. Next up, we have the second method, which is your chain. Method number 2, chain rule. So the chain rule. The chain rule states that for any situation where you have whatever your basic results, you can say that for f of x, g of x, if you're going to differentiate this, then it is going to become the derivative of g f of x times the derivative of f of x. So we have g f of x and f of x, g of x and f of x, and all it means is that you take whatever you have. For example, if you're taking the ln of x, so if you're taking the ln of x and you're going to be putting inside of it, and not take e of x, and a to the n, a x to the n. Well, then you're going to take, first things first, you're going to take your ln of x, do that normally. You have your a x to the n over, it's 1 over ax to the n. Boom. So you do that normally, and then you're going to be multiplying it by the derivative of what's inside, which is going to be a n x to the n minus 1. Boom. Okay, there you go. And then, that's chain rule. Next up, we have product rule, which is a lot easier to write. Product rule. So, the product rule states that for a equation, if you're differentiating u, v, then what you're going to end up getting is going to be u times dv dx, u times v differentiated, plus v times u differentiated, or du dx. And finally, the big manga, which is what you use when you really need to bring in the big guns, and you have a quotient, is when you have u over v. That's the quotient rule, which is going to be du dx times v minus dv, oh, it's more like a u than a v, dv dx times u over v squared. So there you go. So when you're differentiating, you got your four methods. You got your standard method, which is just when they're nice lined up. That's like your firing squad. You're just going to pick them off one by one. You have your chain rule, which is when you substitute inside, you work through the outside normally, and then you work through the inside normally and multiply it by that. Product rule, you split it up, and then quotient rule, you're going to split it up again. Remember to subtract in the middle, and then you're going to put it over v squared. And that, my friends, is more or less differentiation.